In this video, we're going to look at the pipe system call. You can pull up the man page for pipe to get some details on it. Pipe is a system call that takes an array of two integers. Very simple system call. Now you'll notice in C, we pass things by pointers. We don't really know the size of the arrays that we use. So this 2 here is really just for documentation. Then pipe is going to create what we call a pipe in the kernel. It's a unidirectional data channel where we can put data in one side of the pipe, and then we can get data out from the other side of the pipe. So let's look how we can use pipe by writing a simple program. Call it testpipe.c. We'll do the include unistd. This is what we saw in the man page for pipe, and then we'll also include stdio since that is what we will be using to do the printfs. So we'll do the standard declaration of main just to kind of start off our program. Now to use pipe, we need an array of 2 integers. Now these are going to hold the file descriptors, so we'll call this FDS. It's of size 2. Now these file descriptors, the first one, index 0, will be the input file descriptor. That could, of course, I like to think of it as corresponding to standard in, so that's 0. And then 1 will be the output, kind of corresponding to standard out. So then we can call pipe, pass in the address of that array, and then we'll also check and see if there were any errors. So if there's any error, we're going to call pierr, and then we'll exit. Now at this point, we're able to write to the pipe. So we're going to write to FDS1, because that's the writing end of the pipe. And we'll just write a simple string, hello. Now this string is of size 7. That's 5 for the word hello, 1 for the exclamation mark, and 1 for the new line at the end of the string. And then once we've written that to the pipe, we can try reading it. So we'll allocate a buffer to read into. We'll do a read. We're going to read from the file descriptor at index 0 of FDS. That will have the reading side of the pipe. And then we'll actually grab the return code from the read just to see how many characters we've read. And then we'll print the number of characters read. And then we'll write to standard out, which is file descriptor 1, what we've read. And we're going to write RC number of buffers, RC number of bytes. So let's compile this, run it, and see what happens. Oops. Yeah, we need to include stdlib for the exit. There we go. So we see it worked. We wrote 7 bytes into the pipe. We read 7 bytes out of the pipe. and we see that we were able to print what we put in. Now, this doesn't seem all that useful since we already had the string hello, and moving it through a pipe was just extra work. So why do we use pipe? Well, pipe becomes much more powerful when we combine it with fork. When we have multiple processes, when we fork, we create a copy of the process, and we lose this ability to share information between the two processes. However, fork also copies all the file descriptors. So this allows us to have a communication channel between the parent and the child. So we're going to use the writing end, the child will use the writing end of the pipe to write a message to the parent, and then the parent will read from the reading end of the pipe to get that message. So that's what we see here. So here we see that string hello now was sent from the parent, or from the child to the parent, and the parent was able to read it. What if we add another string? Let's put again here. So now we have two strings of length 7 that we're writing. Note we're not passing the nulls. Let's run this and see what happens. So this might be a little bit surprising. We do 2 writes of 7 bytes and 1 read, and we get back all 14 bytes in that 1 read. So you notice this pipe, it doesn't preserve how you did the write. It just collects a bunch of bytes, pushes them through a pipe to the other side, and when you do a read, you're going to get all the bytes available. So what if we add a sleep here? Now, no, it's not really that great to do sleeps for synchronization, but this is just a quick and dirty test. So let's see if we add a sleep, what happens, what changes. So here we see that we only read 7 bytes this time. Now the reason for this is when we did that, when the parent does the read, at this point in time, because of that sleep, the child will have only written the hello. So if we put a sleep in the parent to sleep 2 seconds, we'll see that we get that 2-second sleep. And now again, we read both all the data with the 1 read. You'll note here the child isn't going to ever read from the pipe. So we can close that end of the pipe. Turns out, because of the fork, the parent and the child have a copy of these file descriptors. So in the child, we'll close the read end, and then the parent will close the write end. And now we see nothing has really changed, right? So let's modify this a little bit, and let's move the sleep to after we do both writes. So we're going to sleep 5 seconds. That way we kind of notice the delay. And then we'll just run it just to make sure nothing's changed. Well, we should see a delay, but we don't, right? We added this delay to the child, but we don't see it. Well, that's because the parent has done the reads and is finished. So the child, even though the child hasn't finished, the parent is done reading. So now we've added we've duplicated these read lines in the parent. So now the parent is going to try and read twice from the child. Notice the child is still sleeping for 5. And let's see what happens. So we see the first read completes. We read all 14 bytes. But then there was that 5-second delay for the parent to complete. Now, what changed? Well, we noticed that we didn't get the RC equals 0 until the child completed. So let's take a look at our code again. We see that at line 29, when we do the read, the child has finished writing, but it's sleeping for 5 seconds. So when we do that read at line 29, the kernel doesn't know if someone else is still going to write to FDS0, because the child still has FDS0 open, that file descriptor for the writing into the pipe open. So there could still be something coming in. So until that end of the pipe closes, that read will wait for data to come in. So we can close that end of the pipe after we do those 2 writes. And now both copies of the file descriptors to the right end of the pipe will be closed, and the kernel will know at line 19 that nothing else can write to the pipe. So even though we're going to sleep for 5 seconds, the kernel will know even before the child exits that we're done writing to the pipe. So let's actually do a print of child finished just before the exit, so that we know when the child finishes. And let's run this again and see what happens. So here we see it. We no longer waited. When that second read happened, the kernel knew no one else was going to write. So we got the RC0, and then 5 seconds later, the child finished. So up to this point, we've just been looking at strings and writing bytes. Let's look at writing a number. Now, a byte or a character is a number, but it's only 8 bits, and we usually use strings and character literals for it. So let's do a 16-bit number, short, and let's pass that to the parent. So now we're going to pass the address of num, and num is 2 bytes, so we can pass 2 to write if we wanted to, or we can pass the size of num, which is kind of the nicer thing. Now in the parent, instead of reading into a buffer, we could still read into the buffer if we wanted to, but we'll actually read directly into a variable in the parent, which we'll call parent num. And then we'll go and print the return code, and we'll also print the number we received. Now, since it's 16 bits, we use H before the D to indicate it's a half word, or a short. And then we'll do a second read. We'll try and do a second read just to see what happens, just to see what the return code will be. Now we kind of already have an idea of what's going to happen, because it should behave the same way as it behaved when we did the strings, but let's just make sure. Okay, so there we go. We got the number 7 that was passed up from the child, and we see when we went to read a number again from the pipe, the child had already exited, and all the writing ends of the pipe had been closed, so that second read just returned with 0, since there wasn't anything to read and no one could write to the pipe anymore, so there was nothing to wait for. Okay, so just quick recap. When we read and write from pipes, they kind of work like files. And when we do a read, it tries to read, it blocks until it can read at least one pipe. Now this pipe is actually something you've seen before. When we do this ls and we grep, we search for any, so ls is to list the files, the contents of a directory, and grep is to search for a string. So we're listing the contents of the directory and we're sending the output of that to grep to search for any lines that start with test. And there we see out of all these files, there were 2 that started with test, or that I shouldn't say started, they have the word test in them. And so this becomes a very powerful way in Unix to compose commands. And what's really happening here is the shell is starting up ls and it's connecting its output to the input of grep with pipe.